So guys, what I'm going to do, well, let me give you the topic first. So today, guys, we're going to do what are called Lewis dot molecular structures, which should sound familiar to you because, guys, the last thing on the last test was Lewis dot structures. The difference is now we're going to do Lewis dot structures for molecules, and now you know what those are, molecules rather than individual atoms. So what we're going to do today is we're going to start by reviewing. I'm going to go back to the last slide of the screencast that you watched, help you figure out how we're going to move forward. Then, guys, we're going to recall some stuff from the last unit. Then we're going to establish some groundwork for this. Then, guys, we're going to do 4 examples together, and then the rest of the day today is going to be for you to practice. So you're going to have a bunch of time today to work on homework. You guys ready to go? Okay, so hopefully this looks familiar. Familiar? Okay, did you guys have the time to write this down during the screencast? You guys were good? Okay, so guys, don't write this down again. You don't even need to go back. You don't even need to go back to your notes. Guys, what I want to do is use this as sort of an anchoring point so that you understand how we can move forward. So guys, in review, you should understand this. One of the things that we talked about is ionic bonding. Again, that's a metal and a non-metal. When ionic bonding happens, that leads to salts, and you now understand that hydrogen, even though it's a metal, that doesn't form salts. Nothing can steal from it. You guys all good on this stuff? Okay, then guys, the third thing that we talked about was metallic bonding. You get these metal atoms together, they're big and fat and weak, they all lose their electrons, they form this sea of electrons, this spread out bonding. That's what metals do. You guys good on that? Okay, so guys, why did I mention number 1 and number 3 first? And the reason is because we're done with those. We are not going to talk about salts, and we're not going to talk about metallic bonding anymore this year. We're done. So guys, everything else that we're going to do this year is all about covalent bonding, which is sharing bonding. So this leads to molecules. And so guys, when we draw Lewis dot structures, we're now going to draw Lewis dot structures for molecules because that's the stuff that's covalently bonded. You get the idea? Okay, so guys, with that as a background, we need to review. I don't think you need to write this stuff down, but let's make sure you're clear. Guys, really, don't write this down. So, when we draw Lewis dot structures for atoms, which are the electrons that show up in the diagrams? The valence electrons, right? So let's remind ourselves, how many dots can there be? There can be 8 electrons. So what sublevels are these electrons in? The highest? P and S, yeah, so they're in, or S and P in order. So in the highest S and P orbitals. So guys, how do these electrons distribute? How many electrons are in the S? 2. How many are in the P? Is it all coming back to you? Okay, this is where you want to start taking notes, because this leads us, well, not yet. Let's do orbitals first. So guys, you understand there's 1 S orbital, it's a sphere. There's 3 P orbitals, they're dumbbells. Is that all good? Okay, this is where you want to start taking notes, because all of this brings us to a thing called the Octet Rule. We've been sort of skirting around this for a while, but guys, we need to define it because it's going to be the foundation for what we're going to do today. So what does the prefix oct mean? Am I doing okay? Is this coming out? Seriously, never mind, too much information. I'm going to make it. Okay, so guys, when we talk about the Octet Rule, we're talking about 8. And so when we talk about 8, the Octet Rule says this: when atoms bond, they are most stable when they have a complete shell of 8 valence electrons. That is going to be our guiding principle for the entire day, the entire unit, the rest of the year. Guys, when atoms bond, what they're trying to do is get 8 valence electrons. And so when we start drawing these Lewis dot structures, we're always going to be looking for full shells of 8 valence electrons. That's going to be sort of your goal for the day. You guys good? You okay? Okay, so guys, here's what you need to do. Grab your periodic tables, and if we're going to draw Lewis dot molecular structures, we need to base these on Lewis dot atomic structures. So guys, draw the Lewis dot structures for these 5 atoms. You could probably string them across your page all the way across. But guys, these are the building blocks that we're going to use to draw Lewis dot molecular structures. So I just want you to have the experience again of drawing these Lewis dot structures. And along the way, there's a term that you're going to learn, and then a little surprise at the end. And then, guys, we're going to define some rules, and then we're going to do 4 of these, and then you're going to have a chance to do your homework. And I will find a comfortable place to take a nap. In the old school, we used to have this back office that nobody knew about. It was a glorious place to nap. That's gone now. It's very sad. So guys, again, we're going to do hydrogen, nitrogen, oxygen, chlorine, and carbon. By the way, guys, I don't know if you looked at the calendar or even when I brought it up. So today you're going to learn to do these Lewis dot structures. On Wednesday, we're going to do a whole nother day of these because it's critical that you get good at these. So we've actually scheduled a second day with no new material where you're just going to do a whole nother set of these. These are important. You guys good to go? Can we go through them? Are you there? And you remember that the dots rely on the columns, right? All of them have 1, 2, 3, 4, 5, 6, 7, 8. So guys, how many dots does hydrogen have? 1, right? Doesn't matter where it goes, but it's got 1. So I don't think you need to write this down, but now I'm going to introduce you to a term. So guys, see this spot right here where there's 1 electron but not 2 electrons? That has a name. That is what is actually called a bonding site. If you don't think you can remember that, you can write it down. But guys, that is the place where bonds form, covalent bonds. That is the spot where these bonds form. It's a place where there's 1 and not 2 electrons. So guys, hydrogen then has 1 bonding site. So why doesn't it have 6 more bonding sites around the outside? Well guys, it's got to be 1 and not 2. So these empty orbitals they can't form bonds. It's just 1 but not 2. So now let's do nitrogen. It's got 5 electrons, so it looks like that. Is that what you got? So how many bonding sites does nitrogen have? Good. And that's the thing that you got to be able to identify, guys. Nitrogen has 3 bonding sites. You don't need to draw them in. I put boxes just to draw your attention to them. But guys, you just got to be able to count bonding sites. So guys, looking at oxygen, oxygen's got 6 valence electrons, so it looks like this. How many bonding sites does oxygen have? 2, that's why it forms H2O. So oxygen's got 2 bonding sites. Chlorine's got 7 valence electrons. How many bonding sites? You starting to get the idea? Okay, so guys, now that you understand this pattern, I need to throw you a curveball. So take a look at carbon. Carbon looks like this. How many bonding sites does it have? It's got 2, right? But guys, do this with me. I'm not going to explain to you why this happens. If you want to find out, come back and take AP next year. For this class, you just need to know this. Guys, before carbon forms bonds, these electrons spread out. So this electron in the S sublevel actually jumps into the P and it does that. So guys, cross out carbon and redraw it and spread out its electrons as much as you possibly can. Just 1 second. And I wonder if your question is going to be we'll talk in just a second. So guys, now that you've done that, how many bonding sites does carbon have? Yeah, good, and that's the idea. Go ahead. Let's play this game. Okay, guys, here's what I need you to do. You ready? And the answer is no, but watch. So guys, the question is, does that only happen to carbon? And the answer is no. So now what I need you to do is this. Guys, go back to hydrogen, nitrogen, oxygen, and chlorine and spread out their electrons as much as you can, just like you did with carbon. You done? It doesn't change anything. Check this out. So guys, if you spread out the electron in hydrogen, there's nowhere else to put it. Guys, if you spread out this one electron in nitrogen, you've got to move it to one of these other places, and it ends up being the same. If you do that to oxygen, it ends up being the same. So the answer to your question is they all do this, but it only makes a difference for elements like carbon. Because that's the, and again, the idea is that you'll notice that carbon's got a spot here and an empty spot there, so it can come down and spread out, where these, if you redistribute them, they end up the same. Yeah. Yes, and so and actually it's a really interesting thought. So the question is there a trend to this? And the answer is the only elements that do this are the nonmetals. The metals don't do this. The reason is because the metals don't form covalent bonds, they form ionic bonds. And so the only time this happens is in covalent bonding. And when they covalently bond, that's only the nonmetals. So only the nonmetals do this. But as you said, the only place it makes sense is with carbon, because all the rest of them stay the same. Did that make any sense at all? Because this is like echoing in my head. You guys, please. Silicon does this too. So because they're in the same group, silicon will do this as well. So all of the group 4 elements do this, well, except for tin and lead, because those are metals and they don't covalently bond. But so, yeah, so silicon does this. Germanium does a little bit, because sometimes germanium can form covalent bonds, but that's it. Is that okay? You guys good on that idea? Okay, so guys, now watch what we're going to do with this. So now what we're going to do is we're going to take these Lewis dot structures and we're going to start literally putting them together and forming molecules. Don't write this down until I tell you. So guys, here's what we're going to do. We're going to take an oxygen atom, and again, how many bonding sites does oxygen have? 2. And we're going to take a hydrogen atom, and how many bonding sites does hydrogen have? 1. And you're going to see that these link together like puzzle pieces. So we're going to take these Lewis dot structures for atoms and fit them together bonding site to make molecules. But now guys, you'll notice that oxygen's got another bonding site, so another hydrogen comes in and it does that and it forms water. Does that make sense? Okay, but guys, here's the trick. We are not going to draw these bonds by drawing them as pairs of dots. And watch, this is subtle, but look at what we're going to do. Instead of drawing the bonds as 2 dots, we're going to represent them with lines. So that line represents how many electrons? 2 involved in a bond. So guys, this is what you want to write down in your notes, because we need to label this. So make it like 1 inch across. It doesn't have to be big, but draw it like this. So guys, this is the way we're going to draw Lewis dot molecular structures. We're going to allow lines to represent the bonding pairs of electrons. So let's just label them. So guys, these 2 lines right here represent bonds. We call those bonding pairs or shared pairs of electrons. And then guys, these electrons on the left are what are called non-bonding or lone pairs of electrons. And one of the things that you've got to be able to do today, guys, is count the number of shared and lone pairs of electrons on the central atom. And we'll talk more about that as we go. Bless you. Hey. Absolutely, yeah, definitely, yeah, and you're going to see all sorts of examples. The atoms around the outside don't have to be the same. Yeah, and you'll see that. Go ahead, John. No, it really doesn't. Up and down and left and right, and these don't matter at all. And you're going to find out at the end of this unit that we're going to talk about what they look like 3-dimensionally. Right now, it doesn't matter. So guys, John's question was, does it matter if the hydrogens are on the right or the bottom? And the answer is no. They can be on any of those faces, because these aren't what these look like 3-dimensionally anyway. And then Jessica's question was, do the atoms on the outside have to be the same elements? And the answer is no. And you're going to see bunches of examples of that today and on Wednesday and for the rest of the year. So you guys good on that idea? Okay, so don't write this down, but here's the trick. Guys, what I'm going to do is I'm going to teach you a series of shortcuts that I learned in college. When I learned to do these in high school, my high school chemistry teacher taught us to draw Lewis dot structures by drawing the atomic Lewis dot structures first and then fitting them together just like I showed you as puzzle pieces. And it worked and everything turned out fine. But guys, honestly, it was tedious. And when I got to college, I had a professor that taught me all sorts of shortcuts and easier ways to do these. And I was like, oh my gosh, I wish I'd learned these in high school. So guys, I'm going to teach you the shortcuts. I'm going to teach you how to do these so that you don't have to draw the Lewis dot structures for the atoms first. You're going to find this much easier when you get to college. If you have a professor that doesn't teach you it this way, understand this will always work. You can teach your friends and then you'll be a hero. So guys, these are the rules for writing these things. You want to write this down with me. These are the shortcuts. But again, guys, they always work. So guys, these, and when I say shortcuts, really we're going to treat them as steps with shortcuts sprinkled in. So guys, it goes like this. Step number one is this. Put all the atoms on the paper. Just get them on the paper and single bond them together. And again, guys, I'm just going to give you these steps and then we'll do them for 4 examples and then I'll turn you loose and let you play with them. So guys, step number one is put all the atoms on the paper, single bond them together. Now guys, when you do this, there are some hints that will make you more successful. The first one is this: draw them symmetrically. And I'll show you an example of this in just a second. Do you guys understand the concept of symmetry? Same on both sides, symmetrical. Okay, so let me show you an example. Guys, and don't write this down, just watch, you'll get it. So say, for example, the molecule we're going to do is NO2. So 1 nitrogen and 2 oxygens. There's 2 ways you can do this. You can do it like this, and you can go NOO, but that is not symmetrical. You've got a nitrogen on one side and the oxygen on the other. And guys, nature tends to be symmetrical. So instead of that, you would want to do it like this because that's then a symmetrical molecule. And that's what this molecule looks like. So when you put these things on the paper, do it symmetrically. Does that make sense? Okay, so then guys, trick number 2 is this. Always put carbon in the middle. Why would carbon be in the middle? But what did you just learn about carbon? How many? It's got 4 bonding sites. And guys, that's the most bonding sites there can be. So carbon tends to be in the middle because carbon is the atom that can form the most complicated molecules because it's got the most bonding sites. Yeah. So the idea is that everything that's alive has carbon in it, right? Carbon is the foundational atom for life. So the question is, why is carbon the foundational element for life? Well, it can form 4 bonds, which is the maximum, which means that it can form the most complicated molecules. Now, either nature did this well or God is smart, however you sort that out in your brain. But everything that's alive contains carbon because life is complex and carbon allows for complexity. So the reason that we carbon date things to find out how old it is because if it was alive, it's now dead. But when it was alive, it contains carbon. And we can figure out when it died based upon the amount of carbon-14 it contains, because that's radioactive. But everything that's alive contains carbon. Okay, so guys, third rule is this: the halogens and hydrogen can never be in the middle. And I want to talk about why it makes sense, but I want to let everybody get there. So guys, halogens and hydrogen can never be in the middle. So guys, allow your eye to glance up at the Lewis dot structures that you drew. And so if you're not familiar with this, your halogen is chlorine, right? So what do hydrogen and chlorine have in common given their Lewis dot structures? 1 bonding site. So guys, why can hydrogen and the halogens never be in the middle? Because they can only form 1 bond. So think about it this way. It's sad, but imagine if I had you guys all get up and say, okay, class, we're all going to link hands and sing Kumbaya. Now, guys, if there's somebody in the room that only has 1 arm, I know, sad. Where do they have to be in the chain? On the end. They can't be in the middle because they can only grab hands with one person. Guys, hydrogen and the halogens are like one-armed people. They can only form one link, and as a result, they can't be in the middle. Does that make sense? Okay, so guys, never put hydrogen or halogens in the middle. So once you're done with that, guys, when you're figuring out the order that these bond, many times the bond order will be in the formula. Keep that in mind, that'll help. Oh, sorry. Okay, so we've got 3 more steps. Now that you've got the hints for putting these on the paper, step number 2 is to count all the valence electrons for every atom. And guys, when you do that, watch out for ions. You're going, wait, ions? I thought this was covalent bonding, not ionic bonding. You'll see in a minute. Sometimes molecules can have a charge. Then guys, step number 3 is spread out all the unused electrons evenly around the molecule. And guys, when you do this, you need to make sure that halogen is filled up with unbonded electrons. You've got to fill the halogens with unbonded electrons because there's no other way for the halogens to get 8 electrons other than giving them unbonded electrons. I know that doesn't make sense, but you'll see. And then guys, finally the last step, and I know I'm going fast, this is the end of your notes. When you write this down, number 4, check and fill octets by forming multiple bonds. So guys, I know that was a lot, but when you're done writing down number 4, we're just going to work on 4 of these examples. Take us about 10 or 12 minutes, and then I'm going to get out of your hair, and you guys are going to have the chance to work on these. This is going much better than I thought it would. Yeah. Who could it be? You're back. We waited for you. Actually, we didn't. Because that would have been awkward. But we did tell stories about you. Actually, we didn't do that either. We should have, though. You guys all caught up? Are your hands cramped up? You ready to draw some pictures? You like pictures? You'll like this. You guys good? I don't want to rush you, but I'd love for you to have time to get your homework done. You okay? Okay, so guys, rule number 1 when you're doing these, do them in pencil. You're going to be erasing a lot. You can't do these in pen. So that said, maybe I should provide some pencils. Does anyone need a pencil? Do I dare throw this to you? Come on. Wow, that could have stabbed your eyeball. Does anyone else seriously need a pencil? I won't throw it at you. You guys good? Okay, guys, seriously, do not do these in pen because you're going to be erasing a lot. You've got to have a pencil. I have the advantage of having a digital board, so I can erase really easily, but you guys good to go? Okay, so here we go. So guys, we are going to do 5 examples. In the upper left-hand corner of the screen is the molecule that we're going to draw the Lewis dot structure for. On the right hand of the screen is the place where we are going to write down the shared and lone pairs around the central atom. So guys, the first one that we're going to do is NCl3. So guys, remembering our steps, our hints, whatever you want to call them, step number 1 is put these on paper. So guys, when we do that, we're going to do it symmetrically. So check this out. We are not going to do this because that is not symmetrical. So what could we do to create a symmetrical molecule? We're going to put nitrogen, and then we are going to attach those 3 atoms to the chlorine. So it looks like this. So guys, we've done step number 1. We've put them all on the paper. We've single bonded them together. It's symmetrical. There is no carbon So we don't need to worry about that. None of our halogens, the chlorines, are in the middle because they can't be. We've got this on the paper, so we're good to go. So now, guys, we're ready for step number 2, which is count up all of the valence electrons. So, guys, how many valence electrons does nitrogen have? How many dots did you draw in your picture up above? 5. Do you remember why? So, guys, nitrogen's got 1, 2, 3, 4, 5. So here's what you're going to do. Write a 5 right there above nitrogen. Now, guys, how many dots does chlorine have? 7. It's a halogen, but you'll notice that there's 3 of them, so that gives us 21. Did that make sense? 3 times 7. Okay, now, guys, what you're going to do is you're going to add those up, and that totals to 26. So now we've done step 2, we've counted the total electrons. So now step 3, we are going to spread the unused electrons around the molecule. But guys, we've already used some electrons. What do these lines represent? How many electrons? 2. So we've already got 2, 4, 6 on the board. So subtract the 6, and that leaves us with 20. So now, guys, step 3, we are going to spread those 20 electrons evenly around the molecule. Now, does it matter where we put them? And the answer is no, with one exception. We've got to fill up the halogens first. So, guys, the first thing that you've got to do is fill up the halogens. And here's how you do it. You go 1, 2, 3, 4, 5, 6. Now that halogen is filled. Always fill the halogens first. So that one's got full. Then we go 7, 8, 9, 10, 11. Oh boy, that was a mess. And 11 and 12. Now that halogen is filled. Then we go 13, 14, 15, 16, 17, 18. Now that halogen is filled. And guys, how many electrons have we used? 18. How many did we have to use? 20. So where did the other 2 electrons go? On the nitrogen. So now we've got all 20 unused electrons on the screen. So guys, the last thing that we need to do, step number 4, is check for octets. Now guys, you don't need to write this down. Don't do this for real, but just watch. Here's what checking for octets means. Draw an imaginary circle around the chlorine. How many electrons are inside that circle? 8. 2, 4, 6, 8. So that one's got 8. Guys, how many electrons are inside that circle? 8. That's the octet rule. How many are inside that circle? 8. That's the octet rule. But now, guys, watch this. How many are inside the circle around the nitrogen? Also 8. So we have fulfilled the octet rule for all of these atoms because they all have 8. So now, guys, the last thing that we need to do is count the shared and lone pairs. And guys, we are only going to count the shared and lone pairs around the central atom. So how many shared pairs are on the nitrogen? 1, 2, 3. And how many lone pairs are on the nitrogen? 1. And guys, that will always add up to 4. Go ahead. The lone pairs are these guys, the unbonded electrons. Is that okay? So the shared pairs are the bonds, those are the lines, the lone pairs are these dudes. Is that okay? Guys, questions? Okay, let's do 3 more of these and then I'm going to cut you loose. So guys, the next one that we're going to do is C2H4. Step number 1, get it on the paper. But now, guys, look at the hints. Now these hints count. Like which ones? Carbon goes in the middle. What about hydrogen? Never in the middle. So guys, how can we put carbon in the middle, hydrogen not in the middle, and do this symmetrically? So check this out. We could go carbon, carbon, but then what about this? Hydrogen, 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 hydrogen? What's wrong with that? Yeah, it's got to be 2 and 2 because that's symmetrical. So guys, we're going to go carbon, carbon, hydrogen, 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 hydrogen. Now, does it matter if you put the hydrogens up or down or left or right? Doesn't matter. You guys good? Okay, now what's step number 2? Count electrons. So guys, how many valence electrons does carbon have? What group is it in? 4. So it's got 4, but that's times 2 is 8. Now how many electrons does hydrogen have? 1 times 4 is 4. So guys, that leaves us with, that gives us 12. Now, how many electrons do we already have on the board? 2, 4, 6, 8, 10. So guys, that leaves us with 2. Now, don't write this down because this is wrong, but check this out. What's wrong with that? Hydrogen can only have 2 electrons. Hydrogen doesn't have a p sublevel. So guys, you can't put any more electrons on hydrogen. Hydrogen's done. So where do we have to put the electrons? On carbon. And it doesn't matter where you put them. Guys, you could put them both there. You could put them both on the right. Doesn't matter. Keep them together as pairs, but it doesn't matter where you put them. Okay, so now guys, last step, we need to check the octet rule. So don't do this. Don't check the octet rule for hydrogen because it doesn't fulfill the octet rule. It can only have 2 rather than 8. So now let's do the octet rule for carbon. How many electrons are in the circle? 8, so that one's done. But now guys, what about this? How many electrons are in that right-hand circle? There's only 6, so that carbon's not done. So what we've got to do is we've got to figure out a way to give carbon more electrons, but we're out of electrons. So what are we going to do? Check it out. We are going to take these 2 electrons off, and we are going to push them into the middle and form a double bond. Let me show you. Guys, it actually looks like, wait for it. Oh boy. It looks like this. So what you end up with, and by the way, you're going to have these model kits next week. You guys are going to be building these. So guys, it actually looks like this. So this is what this molecule looks like. There's a double bond between the carbons and then 4 hydrogens, and this thing's flat, and it looks like so. So this is C2H4. And now when we check the octet rule, you'll notice that we've got 4 here, and we've got 4 there, and that dude's happy. Does that make sense? Okay, so now guys, the last thing we need to do is we need to check for how many shared and lone pairs. And guys, this is the rule. You only do it for the central atom. Now, which one is central if both of these carbons is in the middle? And the answer is it doesn't matter. Just pick one or the other because they're the same. Don't do it for both. So let's say we pick that one. How many shared pairs are on that carbon? 4. 1, 2, 3, 4. So that's got 4 shared pairs. How many lone pairs? None. There are no unbonded electrons. But guys, either you do it for one atom or the other, not both. Go ahead.
When you add additional electrons to make the double bond,
Yeah. Good.
Did that indicate an ion?
No, because we didn't remove them, we just moved them. Let me see if I can back up that far.
Oh, yeah.
Because what we did, that's as far as I can go. Yeah, John, that's an interesting question because we didn't actually remove the electrons. They were originally there. And what we did is we moved them from there into here. So we didn't take them away. We just pushed them into the middle. You guys good? Okay, so let's do 2 more. And then you guys are going to have time to do your homework. So guys, the next one we're going to do is this. NO3 with a -1 charge. So what does this mean? Well, guys, this means that this molecule has a charge. And that happens. We're going to talk about this more after Christmas, but for now, you just need to understand that this is a molecule. It's nonmetals, it's covalently bonded, but this entire molecule has a charge. So this is an NO3 molecule with a -1 charge. So how do we deal with this? Just like any other molecule. So guys, we've got to get this on the board. We got to get this on the board. Oh, I clicked. Sorry. Guys, we got to get this on the board and symmetrical. So we've got N and O, and I'll put this, I'm struggling. I've done pretty well up until now, though. So guys, we've got N and O and O and O. So there we go. Is that okay? So now guys, step number 2, we need to count valence electrons. Is it okay if I just say nitrogen's got 5? What about oxygen? How many does that have? 6. The halogens are 7. Oxygen's got 6. It's in the 6th column. But notice there's 3, so there's 18. But now guys, check this out. What does it mean if a substance has a -1 charge? How do we make a -1 charge? Add an electron. So that's the only difference, is that gives us an extra electron. So now what are we going to do? We add them up, and that's 24. So how many electrons are already on the board? 6. And that leaves us 18 electrons. So guys, now what we've got to do is spread these 18 electrons around the molecule. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So guys, I'm going to get this out of the way just because it's sort of in the way. Okay, so we've got that. Now let's check the octet rule again, guys. You don't need to draw these circles, but I'm going to. How many has that guy got? He's good, right? How about this one? 8. How about this one? 8. So guys, those are all good. But what about the nitrogen? Nitrogen's only got 6. So what can we do to give the nitrogen 8? Form a double bond, but the question is where? It doesn't matter. You could go to any of these oxygens. I'll just go to the one on the right because it's closest. And we're going to take 2 electrons off and we're going to push them into the middle. And now everybody's got 8. And this actually looks, let me build it for you. This actually looks like this. Just like so. So guys, this is actually what this molecule looks like. It's called NO3. It's called nitrate. But this is what this looks like. Yeah. No, everything there's got 8. So if you look, this has got 8, this has got 8, this has got 8, and that's got 8. So the octet rule counts for everybody, except for hydrogen. Hydrogen violates the octet rule, none of the rest. Yeah, exactly. Is that okay? So guys, one last thing that we need to do this with me. So this is an atom, or I'm sorry, this is a molecule that has a charge. So there's one more thing we've got to do. Do this with me. Put it in brackets and add the charge. And then guys, let's do shared and lone pairs. How many shared pairs are on the nitrogen? 4, and lone pairs are 0. You guys liking this? Not too bad, right? Can we do one more? Let's do one more. Here we go. Carbon monoxide. Horrible stuff. So guys, we're going to draw the Lewis dot structure for carbon monoxide. So we don't have a lot to put on the board. We've got a carbon and we've got an oxygen. What do we do next? Count electrons. So guys, we've got 4 on carbon, we've got 6 on oxygen, so that gives us 10. What's next? Subtract the number that we've already got on the board, and that would be 2, so that leaves us with 8. So now guys, what are we going to do with those 8 electrons? Well, we're going to spread them out. Let's do it evenly, so let's go 4 and 4. So we'll go 1, 2, 3, 4, 5, 6, 7, 8. So what's the last thing we do? Octet rule. So guys, is carbon happy? No, it's only got 6. Is the oxygen happy? Also not happy, it's only got 6. So let's solve this one at a time. Let's take 2 off of the carbon and push that into the middle. Now is the oxygen happy? The oxygen. Take a look. Does oxygen have 8? It does. But what about the carbon? No, the carbon's only got 6. So now we need to give the carbon more electrons. So now we'll pull 2 off of the oxygen, move that into the middle, and now we've got this dude, which is carbon monoxide, and that's actually triple bonded. And guys, that's the limit. There are no quadruple bonds, but that's what a triple bond looks like, and this is carbon monoxide. Not too bad. So guys, now let's do shared and lone pairs. Which atom are you going to choose as central? Doesn't matter. Could be the carbon, could be the oxygen, because in either case, it's 3 shared and 1 lone pair. You guys good? 25 minutes you've got. So guys, grab your homework packets and let's talk. Hey, so guys, be careful. Don't do assignment 4. It looks exactly like assignment 3. They're the same. But don't do 4. The ones on 4 are a lot harder than 3. So guys, make sure you're doing assignment number 3. There are 20 of these. You're going to draw their Lewis dot structures. I would strongly encourage you to do this on another sheet of paper. You're going to need space. Guys, I will put the answers up here on the wall. I'd love to be available to you if you need help. So please ask questions, dig in. You may actually get this done. So guys, let's dig in and see what we can do. Just one second. Let me finish recording here.